Principal component analysis is an essential dimensionality reduction algorithm. It entails lowering the dimensionality of data sets to reduce the number of variables. It keeps the most crucial information in this manner. This method is a helpful tool capable of several applications such as data compression or simplifying business decisions. Keep watching if you want to learn more about this algorithm. The first thing we are going to do is import all the datasets and functions we are going to use. For a high-level explanation to the scientific packages, NumPy is a library that allows us to use mathematical functions. This will help us to operate with the matrices also available thanks to this library. Seaborn and Matplotlib are both used to generate plots and graphics. Matplotlib is also used as an extension of NumPy, including more mathematical functions. sklearn is the reserved word for scikit-learn, a machine learning library for Python. It has some loaded datasets and various machine learning algorithms. Next, we will declare a class called PCA. The focus of this algorithm is to reduce the dataset to make it simpler while retaining the most valuable possible information. Simplifying the dataset makes it easier to manipulate and visualize the data, resulting in quicker analysis. How is PCA possible? There are multiple ways to calculate PCA. We are going to explain the widely used eigendecomposition of the covariance matrix. An eigendecomposition is the factorization of a matrix in linear algebra. We can use the mathematical expression to represent this through the eigenvalues and eigenvectors. Having this in mind, let's dive further into the 5 steps to compute the PCA algorithm. Standardization is a form of scaling in which the values are centered around the mean and have a unit standard deviation, allowing us to work, for example, with unrelated metrics. It means every feature is standardized to have a mean of 0 and a variation of 1, putting them in the same scale. In this manner, each feature may contribute equally to the analysis regardless of the variance of variables or if they are of different types. This step prevents variables with ranges of 0 to 100 from dominating the ones with values of 0 to 1, making a less biased and more accurate outcome. Standardization can be done mathematically by subtracting the mean and dividing by the standard deviation for each variable value. The letter C represents the standard score. Once standardized, every feature will be on the same scale. The covariance matrix is a square matrix that displays the relation between two random features, avoiding duplicated information since the variables we are working with sometimes can be strongly related. Let's imagine we have milk and coffee. They are different drinks that people usually drink. In conducting a survey, we can ask some people which beverage gives them more energy, noting their score from 0 to 5. The results will be the data points we can collect to build our covariance matrix. The following table represents collected data from 3 subjects, having 2 variables, C and M, that identify coffee and milk, respectively. This table can be represented in a graph like the following. As we can see, the horizontal axis represents coffee, while the vertical axis represents milk. Here we can notice some vectors created with the values shown in the previous table, and every vector is labeled according to a subject's answers. This graph can be represented as a covariance matrix. A covariance matrix with these features will compare the values each feature has and will proceed with the calculations. Is calculated by transposing the matrix A and multiplying by itself, then dividing by the number of samples, represented as the formula below, resulting in matrices like this. We have 2 instances of covariance matrices here. One is a 2 by 2 matrix, while the other is a 3 by 3 matrix, each with the number of variables according to its dimension. These matrices are symmetric with respect to the main diagonal. Why? The covariance of a variable with itself represents the main diagonal of each matrix. Also, we have to take into account that covariance is commutative. That way, we see that the top and the bottom triangular parts are therefore equal, making the covariance matrix symmetric with respect to the main diagonal. At this point, we need to take into account the sign of the covariance. If it's positive, both variables are correlated. If it's negative, they are inversely correlated. We will compute the eigenvectors and eigenvalues of the matrix from the previous step. That way, we are going to obtain the principal component. Before entering into the process of how we do this, we are going to talk about these linear algebra concepts. In the realm of data science, eigenvectors and eigenvalues are both essential notions that scientists employ. These have a mathematical basis. An eigenvector is a vector that represents an approximation to a large matrix. This vector won't change by any transformation. Instead, it becomes a scaled version of the original vector. The scaled version is caused by the eigenvalue. That's simply a calculated value that stretches the vector. Both come in pairs, with the number of pairings equaling the number of matrix dimensions. Principal components, on the other hand, being the major focus of this approach, are variables formed as linear combinations of the starting features. The primary goal of the principal components is to save the most uncorrelated data in the first component and leave the remainder to the following component, to have the most residual information and so on until all the data is saved. This procedure will assist you in reducing dimensionality while retaining as much information as possible and discarding the components with low information. With the principal components established, the only things left to do is calculate the proportion of variation accounted for by each component. It is possible to do this by dividing the eigenvalues of each component by the sum of eigenvalues. A feature vector is a vector containing multiple variables. In this case, it is formed by the most significant principal component, which means the one with the vectors corresponding to the highest eigenvalues. The number of the principal component we want to add to our feature vector is up to us and up to the problem we are going to solve. Following the same example of the last step, knowing that 1 is greater than 2, our feature vector can be written this way. Also, we know that our second vector contains less relevant information, which is why we can skip it and only create our feature vector with the first principal component. We need to take into consideration that reducing our dimensionality will cause information loss, affecting the outcome of the problem. We can discard principal components where it looks convenient, which means when the information of those principal components we want to discard is less significant. Because the input data is still in terms of starting variables, we must utilize the feature vector to reorient the access to those represented by your matrix principal components. It can be done by multiplying the transposed standardized original dataset by the transpose of the feature vector. The next step is to implement this PCA class. We are going to initialize the variables we are going to use. Here we can notice we are using the datasets library, extracted from scikit-learn. Then we assign those values to our variables. Scikit-learn comes with various datasets. We are going to use the known toys datasets. These are small standard datasets used mostly in algorithms, examples, or tutorials. Specifically, we are loading the diabetes dataset. According to the authors, this data is based on 10 baseline variables: age, sex, body mass index, average blood pressure, and 6 blood serum measurements were obtained for each on n equals 442 diabetes patients. To initialize the class and start calling out the functions of the class. To watch the differences between the original datasets, we can just call the first two functions of the class, throwing the next scatter plot. If we do the whole PCS process, we can better visualize the data in this way. Now we have learned about the key computing procedures, which included some crucial linear algebra bases. Principal component analysis is a straightforward yet powerful algorithm for reducing, compressing, and untangling high-dimensional data. It allows us to isolate the data more clearly and use it for various machine learning methods. Since the original data was reduced in dimensionality terms, retaining trends and patterns, we can notice that the final output of this algorithm is easier to manipulate, making further analysis much easier and faster for the machine learning algorithm, allowing us to forget unnecessary variables and some problems like the curse of dimensionality. Next step is to use your new transform variables with other machine learning algorithms to better understand your data and finally finish your research. If you want a general guide on the existing different machine learning methods and when to use them, you can check a previous entry on machine learning algorithms by LXAI team member Anthony Barrios. Make sure to follow him and the LXAI team. Subscribe to the channel for more AI, machine learning, and data science tutorials to come. See you next time.